Hi everyone. Today I'm going to be talking to you about some of my work using numerical models as a tool to understand bar kinematics in multi-threaded river systems. Before I begin, I'd just like to thank NASA and AGU for sponsoring this award, my advisor Liz Haydiak and Sinead Lister and Rick Donslaw for assistance and guidance in the field. I wanted to start with this photo that shows an exposure of the Huesca fluvial fan system in northern Spain. Now, each one of these ledges in the photo that are highlighted by these dashed lines and white arrows represent different channel belts, which indicate different periods of fluvial activities. Outcrops like these are particularly valuable to us as earth scientists because they contain multiple scales over which we can observe the rock record. For example, we can look individually at each of these channel belts to understand the internal channel dynamics. We can look vertically in time through the section to assess how the system changes and evolves. And then we can also consider how the exposure changes through space. By combining these multi scale observations, we can gain insight into how Earth's surface changed and evolved in the past. And these observations help us greatly in informing models of future landscape change. So, a lot of our context for how these fluvial systems evolve comes from observations with active systems, and satellite imagery is a great resource for doing so, as we get to observe these systems in space and time. So, what I'm going to show now is a time lapse using satellite imagery over the Irrawaddy River in Myanmar. And this is about a 50-kilometer long reach. And I want to specifically draw your attention to the bars in the system. In this 40-year time span, we observe a range of bar kinematics across the reach. If we focus in the upstream section, we can see bars that are constantly being created and deformed and reworked. We also see them migrating and colliding with others in the system to make larger amalgamating compound bars. Highlighted by the blue are regions where we see bars continuously accreting laterally across the channel domain. Then we see one appear and migrate downstream, and the whole cycle is repeated. And then finally, we can look downstream and we see more pulse growth of this bar, which accretes as other sediment packages are sort of piled onto it and smeared around the perimeter of the bar. These time lapses highlight the range of bar kinematics and channel dynamics that occur in relatively small spatial scales and on multi annual timescales. And so my research is focused on understanding the degree to which these bar kinematics get preserved and the implications of these preservation dynamics on how we would interpret the stratigraphic record. I use numerical modeling as my main tool for this work. So what we're looking at now is a video show of a simulation done using the numerical solver NASAEarth 2DH, and it simulates the evolution of a multi-threaded river under constant discharge conditions. So this is a 10-kilometer long reach, and the blue colors represent channels, and the tans represent sediment. Very much like the Irrawaddy, this system and this model run is very dynamic. There's reaches of the system that are categorized by more stable threads that don't particularly change position through time, or they just widen while maintaining their shape and maintaining their structure. And then there are parts of the system that are characterized by more diffuse channels that relocate persistently throughout the channel, throughout the model domain. So you can see those sort of persistent areas here, and then the more diffuse threads at this area, and also within this middle region of the channel. So I use topography that results from this model to construct stratigraphic cross sections, like the one that's pictured here. So what I have shown on this slide here is a final snapshot of the model plan form at the top, and we're taking a cross section right along this region from L to R. L is the left bank, and R is the right bank. And the stratigraphy that we produce from it, we can color it by time. We can color it by different attributes of the flow and get a sense of how those change both in time and in space in the channel. So we can look at that stratigraphy again, like I said, colored by the characteristics of the flow throughout the model run. So what I have colored on here is that same stratigraphic cross section located again from L to R. But here we have it colored first by flow velocity, and then I have it colored by flow depth at the time that sediment was deposited. And we can use knowledge of flow depth, flow velocity, sediment supply, and also shear stress conditions in the channel to reconstruct zones of bed form stability within the channel where we can predict where we would find particular bed forms in the channel. And we use these bed forms to produce what I'm referring to here as pseudofacies in the stratigraphy. So we can see here that the stratigraphic cross-section is characterized by dunes, upstage plain bedding, and also ripples, and then also some lower stage plain bedding again within the section. So we can use the assemblages and the architecture and the organization of these different bed forms to produce these facies assemblages, and we can use the insights that we get from the channel and actually observing how the model run evolves through time to get a sense of what sort of channel dynamics and bar kinematics produce specific signatures in the stratigraphy. And that's what I'm going to show over the next set of animations. So on the left here, we have a zoomed in vision of the channel platform as a simulation evolve, and the plot on the right shows a stratigraphic cross section that evolves as the simulation runs. So this section is located along the white dashed line shown on the plot to the left, and our blue and tan line on the plot to the right is just like our blue and tan in the planform models. It shows where the flow velocity is highest versus lowest, and where we might get erosion and deposition in our stratigraphy based off of where the channel is flowing. So this animation is showing bar deformation and reworking. And throughout the animation, we see bar scale topography that is evolving and then gets reworked at a later time step, resulting in poorly organized units, a lot of bar toes, a lot of cross-trough strata, and also a lot of high shear stress facies. And we'd expect these units to have poor internal organization and be rich in dunes and ripples in actual rock record when we go to the logbook. In contrast, we see zones of relative thread stability within this animation. And in this, we see bars that are accreting and expanding steadily through time. So we see this very steady migration of the channel thread and this bar that grows through time. And you can see that stratigraphically in the picture in the animation on the right. You see these very nice textbook bars laterally accreting across the channel domain, giving us these very nice and well preserved sigmoidal clinothems and clinoforms that we recognize both in the field as sort of our A grade, well preserved bar deposits. So we can additionally observe cases where the stable threads move across the channel belt more sporadically in sort of what I'm terming as pulse widening. And these pulse events produce similarly persistent bars, but they have a higher proportion of shear stress species, so more dunes, more upstage plane bedding than the one I showed previously on the last slide. Um, and these units are best recognized by having undulating bases that form as the channel threads sort of incise into the underlying strata. And you see those underlying undulating bases as the channel sort of incises into the floodplain as it makes its way across the floodplain. So you see those bases sort of forming in the animation here as it goes as the channel evolves through time. So with these species and architectures in mind, we can test these observations within the field area. So we're now looking back in the field. We're back in the Westcafan, like I showed earlier. And what we're looking at is one of those channel belts in the system. And we can see that this belt is characterized by all three of those different facies, forms, or assemblages that we see produced in the model. We have sort of the poorly organized, lack of internal structure, um, dune rich and ripple rich facies that are characterized by that deformation and reworking deposit. Or that reworking style of kinematics. We have more organized kind of forms that sort of accrete very nicely onto that orange body, and then also over the top of this section, obliquely off to the left of the plane, and that we would consider our steady bar growth indicators, where there's steady widening and sort of stable channels. And then we also see this undulating base and this high shear stress species rich section here that's colored on in the purple that might suggest something more similar to that pulse bar growth end member, where we have a channel that sporadically changes its position and widens, incising into the floodplain or whatever strata is underneath it. And so to end, I just wanted to zoom out to the scale that we started at, and we're looking at the set of channel belts in the Wascafan that preserves stratigraphic snapshots of how these rivers interacted and responded to landscape changes in the past. Um, and we can complement this with observations of active systems in the satellite imagery that kind of frame of our understanding of the scale and style of kinematics that we'd expect in these rivers as they respond to changes in their hydrology. And then finally, on numerical simulations and data visualizations of stratigraphy and river planform, help us to tie these two observational end members together, reanimating the rock record and acting as a new lens through which we can connect process to product in the interpretations of the stratigraphic record. Thank you for listening.